Hello, my name is Changmin Oh from ASU. I'm a mechanical engineering undergrad in the Fourth Blossom program. I am working under guidance of Professor Bumjin Kwon. Today, I will show how I used particle image velocimetry to visualize flow around pin pins and how the choice of PIV setting changes what we see. Particle image velocimetry, which is PIV experiment, is an optical technique that measures the velocity field in a laser sheet. We see the flow with tracer particles, fire two laser pulses, and compare two images to compute velocity vectors. In pin-pin channels, this reveals wakes and shear layer. Pin-pins arrays are widely used in gas turbines, power electronics, and other compact systems, so accurate PIV measurements are valuable. I asked two questions. First, what is the optimum interrogation area in PIV measurement? Second, how does the choice of time between pulses impact particle displacement and velocity calculation in PIV? These choices change the outcome. So interrogation area and grid step set the balance between resolution and noise. Time between pulses, if it is too small, it lays noise, and if it is too large, it causes decorrelation. For success, I look for a high valid vector percentage, a low noise level, and a consistent color scale across comparisons. The interrogation area is that we divide the frame into many small windows, in each window we compare the two images to find the average particle shift and turn that into a vector. Smaller window add details but raise noise. Larger windows reduce noise but soften the shear layer. The grid step is the spacing between velocity vectors. In this work, the grid step is about 50% of the minimum interrogation area. The goal is to scan interrogation area and grid step pairs to balance resolution and noise, and to find a lowest setting near the pinwells. I keep the grid step at 50% of minimum interrogation area to avoid oversampling, and the matrix covers small, medium, and large windows from 8 by 8 up to 96 by 96 pixel with grid step of 4, 8, and 16 pixels. Larger windows usually lower noise, but can smother the shear layer, while smaller windows sharpen details but raise noise. All results I show later use the same color scale, so difference come from the setting, not come from the color map. Time between pulses, which is delta t, is the time between the two laser pulses that form each image pair. If time between pulses is very small, particles hardly move and noise dominate. If it is very large, particles will leave the window and the correlation fails. I tested 4,000, 6,000, and 8,000 microsecond at the same linear number, which is 500, while keeping interrogation area and grid step size. For methodology, we use degassed deionized water, which is DI water, as the working fluid. We added 20 micron polyamide tracer particles at about 1.25 milligrams per liter. At 532 nanometer laser, which is make a thin light shift from above. Like here's the green laser. A CC camera looks straight at the seat through the side wall with a 28 microsecond exposure. The water flows left to right through the acrylic pin channel. The laser and the camera were synchronized to capture a pair of images separated by time between pulses. From this slide, on the left, you can see our lab setting with the camera looking straight at the laser sheet from side. On the right is a close view of the pin channel where the flow passes between the pins. The water came through left inlet and it goes to right outlet. You can see the pins inside of the channel. And this is the plane where we place the laser set and capture the two images for PIV. From this slide, I will show you a few short videos that change two things: the interrogation area with the grid step and the time between pulses. Everything else stays the same and the color scale is the same. Please watch three things as the clip learns. First, noise or speckle. And second, continuity of vectors in the wake and near the wall. Third, how sharp the shear layer looks like. In this clip, flows move in the direction of flows flow moves in the direction of arrow. The red box mark the pin location and the near world regions. The color map shows velocity in the channel. Red and orange are higher speed, yellow is moderate, and blue is slower speed. So with a small interrogation area and grid steps of 4 pixels, I see speckle and gaps. Moving to grid step 8 pixel with interrogation area 16 to 64 pixels, it reduced noise. Extending to 96 pixels, it keeps the wake continuous and the shear layer readable. With grid step 16 pixel and minimum interrogation area of 30 pixels, the field is quiet, but the shear layer becomes too smooth, and near the pin start to fade. At 6,000 microsecond, the displacement between frames is larger. Smaller interrogation area cases lose more vectors. And grid step 8 pixel interrogation area 16 to 90 pixel remains readable, but some fine details soften. Grid step 16 pixel is very smooth at this timing, but gradient blur near the upper shear layer. At 8,000 microsecond, the high velocity core shifts almost a pin width between frames. I see dropout and blue gaps along the shear layers, which indicate decorrelation. Even with larger windows, many vectors are lost. The field looks patchy and fine makes details blur. This clip summarizes the effect of interrogation area with time between pulses held fixed and a single color scale. On the left, smallest window captures tiny eddies but but noise is high and vectors near the pins are patchy. On the right, the largest windows are quietest but they blur the shear layer. So I think the best balance is grid step 8 pixels with interrogation area 16 to 96 pixels. It gives continuous vectors, a clean wake, and readable pictures near the wall. Now I hold interrogation area and grid step at the balance setting and change only time between pulses. At 8,000 microsecond, the core jumps far and gaps appear. At 6,000 microsecond, gaps are fewer, but some details fade. At 4,000 microsecond, the vector stayed continuous and the wake is fully resolved. Time between pulses controls how far particles move between frames. Very large time between pulses, it causes loss of correlation. Very small time between pulses, it gives displacement that are too small, which raises noise. In this test, the best continuity and the best readability occur at 4,000 microsecond. Here's quick summary. At 4,000 microsecond, the wake is clean and fully resolved. At 6,000 microsecond, there are minor gaps near the pin wall and the upper shear layer, but the wake is still readable. At 8,000 microseconds, many vectors are lost and fine details blur. Best acquisition combination in this data set is time between pulses equal to 4,000 microseconds, grid step equal to 8 pixels, and interrogation area from 16 to 96 pixels. This gives a smooth and complete velocity fields across the pinkin wake. Time between pulses gives a clear but moderate shift. The minimum interrogation area preserved gradient near the wall. Access to larger windows. Access to larger window strengths, the correlation in low seating regions. The gridded step of 8 pixels aligns with 50% of the minimum window, so it avoids oversampling and also avoids excessive smoothing. For future work, I will test shorter pulse gaps below 2000 microsecond with time reserved or pace-locked acquisition to track vortex paths, and measure shedding frequency. I will also extend the Lehner number from about 300 to about 2500 to map wake evolution and identify the onset of shedding. Here's the references. Thank you for watching.